Hello, grade 12s. My name is Mukasvanga, and I would like to welcome you to our grade 12 STEM in Action Boost series. We're going to start with organic chemistry part 1. So when you look at organic chemistry, the introduction, right? So the main constituents elements of organic chemistry are carbon and hydrogen. But the most important element between the two is actually carbon. And most of the uh, bonds that you get are going to be bonds between a carbon and a hydrogen. So you get compounds such as methane, and methane is actually one of the simplest organic molecules. But you also get what are called substituents. So substituents are when we replace a hydrogen in a hydrocarbon backbone, and we replace it with such elements such as chlorine or oxygen, and we'll get what is called a substituted compound. So if you look at the compound that we have, you realize that if we compare the first compound, the methane compound, we have replaced this hydrogen here represented by an X, where the X will represent either chlorine or oxygen or any other substituent atom. But also note that the X can also represent not just a single atom, it can also represent a group of atoms. So if you look at these compounds, we can come up with the physical properties of organic compounds. And the physical properties of organic compounds are based on these factors which we are going to look at. So if we look firstly at the images that have started showing up, we'll notice that for carbon we have got our atomic number, which is 6, and we have got our mass number, which is 12, and most relevantly, the electronegative value, or electron affinity value, which is 2.5. And what you notice is that the electronegative difference between carbon and hydrogen is very small. In this case, it's about 0.4, which is below 1.7, which means that a bond between a carbon and hydrogen is going to be a covalent bond. And also, if you compare the electronegative difference between carbon and chlorine, or carbon and oxygen, you also notice that the difference is also less than 1.7. Between carbon and chlorine, you have electronegative difference of 0.5. Between carbon and oxygen, you have an electronegative difference of about 1.0, which are also both, in both cases, they are less than 1.7. So the bond that you form between carbon and these substituent elements is going to be a covalent bond. And also, because if you compare the electronegative difference between carbon and hydrogen, we said that it is about 0.4, and that is very small. And as a result, the bond between carbon and hydrogen is a non-polar bond. Therefore, most compounds that contain only carbon and hydrogen tend to be non-polar compounds. Whereas the bond between carbon and these two substituent atoms, the electronegative difference is slightly higher. And as a result, you get bonds that tend to be polar. So bonds between carbon and most of the substituent atoms tend to be polar. And because of that, you get physical properties that are based on the two factors that we have looked at. The first one being that when we have got non-polar molecules, the type of intermolecular forces that form between the molecules is going to be the weak van der Waals forces. Whereas if we have got a polar bond, we then are able to form stronger dipole-dipole moments, such as hydrogen bonding. And because of that, compounds that consist only of carbon and hydrogen, they tend to have weaker intermolecular forces, which results in low boiling point, low melting point, which also means that you get high vapor pressure, and you also get high flammability. And also, such compounds, they tend to have low solubility in water because of their lack of polarity. Whereas compounds that are substituted, which tends to be polar, will form stronger intermolecular forces such as hydrogen bonding. And because they are slightly stronger, you get slightly higher boiling points, you get slightly lower vapor pressure. You also get slightly a lower flammability as a result. And also, they tend to be more soluble in water because water is a polar substance, and if you have got a polar substance, it tends to dissolve better in water. Moving on, this is the periodic table, and you are all familiar with the periodic table. And I would like to identify carbon in the periodic table, which is in group 4 of the periodic table. And what you notice is that because carbon is in group 4, it means that it has a valence of 4 electrons in the last shell. As a result, it requires 4 electrons to be able to form a stable octet state. And because of that, as we shall find out, carbon is able to form 4 bonds around itself. But looking at the periodic table, we'll realize that because carbon is right in the middle, it can form ionic compounds with elements to its left, such as compounds such as calcium carbonate, where carbon is existing in an ionic compound, or you can also form metal carbides, where carbon bonds with a metal to form an ionic compound. But for organic chemistry, carbon will be bonding with nonmetals to its right. Of particular interest is going to be the oxygen, which is in group 6. And we mentioned chlorine already, but chlorine here represents the halogen compounds in group 7, fluorine, chlorine, bromine, and iodine. And please note, hydrogen is on the left side of carbon, but hydrogen is a nonmetal, therefore it also forms covalent bonds with carbon. So what are some of our sources of carbon? Our primary source of carbon are plants and animals. So we can regard this as a fresh source of carbon. Then there is a really, what we can describe as an old source of carbon, which are fossil fuels. And these are found underground. And originally, they also came from plants and animals that were deposited underground, and they formed over a long period of time until they became fossil fuels. Shown here is a trolley of coal, which is a solid fossil fuel. But you also get crude oil, which is a liquid, and you also get natural gas, which comes out as a gas from underground. So those are some of our sources of carbon. And so what makes carbon to be a special compound? If you look at this compound, it is a very complex compound. And for grade 12, you don't necessarily need to know such a complex compound. You only need to know compounds that have got a parent chain of 8 carbons. So this one, you realize that it is more than that. But it highlights the 4 properties of carbon that makes it a very special element. The first one is covalent bonding. So we have already mentioned this and said that because of the position of carbon in the periodic table, it is able to form covalent bonds with nonmetals. All right, the second one, it is a valence of 4. So as we have already indicated, because of the position of carbon in the periodic table in group 4, it is able to form 4 bonds around itself. So if you look on this compound, you will notice that this carbon here has got 4 bonds around itself. And so does every carbon that is represented in this structure. But something special about carbon is that if you look at this first carbon, you notice that carbon has 4 bonds around itself, but it is surrounded by 4 atoms. Whereas in this carbon still has 4 bonds around itself, but this time it is surrounded by 3 atoms. And for this carbon, it still has 4 bonds around itself, yet it is surrounded by only 2 atoms. And in that regard, carbon is able to form single bonds, double bonds, or triple bonds, right? And in all cases, it maintains 4 bonds around itself, but does not necessarily have 4 atoms around itself. The third point is catenation. So catenation simply refers to the ability of an atom to bond to atoms of its kind to form a series or a chain. So as you can see here, we have got carbon bonding to another carbon to form a chain like that. So we've got this chain, we've got that one going down, and that ability is called catenation. And carbon is not necessarily the only element in the periodic table that has this capacity. So elements such as silicon can also do this, but carbon is special in the diversity of compounds that can arise from its ability to do catenation. So you can have, like in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, and you can link them up and have 100 carbons. You can have 1,000 carbons. In fact, the compound compound that has got the largest number of carbons arranged in such a series chain is about 6,000 carbon atoms arranged as a chain. Substituents, right? So we said substituents is when we replace a hydrogen in a carbon-hydrogen structure or a backbone structure. So we replace hydrogen with either a single atom, such as we have with chlorine here, or we can replace it with a group of atoms, such as we have here with the hydroxyl group. Or also this one, which is the methyl group. So these are substituents whereby we are replacing where there was a hydrogen, we replace it with either an atom or a group of atoms to form substituents. So these four properties, because of them, carbon is able to form a diversity of compounds, and there are almost 9 million non-organic compounds, which are different one from the other, both in property and in their chemical expression, arising from the ability of carbon to express itself in different ways, as we have shown. We are going into some definitions. The first definition we are going to look at is functional group. So a functional group is a specific group of atoms and the bonds between them that are responsible for the characteristic chemical reactions and physical properties of those molecules. So if you have got a large organic compound and there is a part of that organic compound which is responsible for the chemical properties of that organic compound, it simply means that when you react the organic compound, when it performs in a chemical reaction, the reaction only happens on that part of the molecule, which is the functional group, and not so much on anywhere else part of the molecule. And also, the functional group influences not only the chemical reactions that an organic molecule can do, but also the physical properties of the organic molecule. And because of this, we are able to classify organic molecules into different classes or families based on what functional group they possess. So looking at that, the first compound we are looking at is this functional group. So the functional groups are going to be highlighted in blue in the chemical structures. And the first one, that's an alkene, right? The double bond is the alkene. So when this molecule reacts, the reactant, if you react this compound under specific conditions, the only part that is going to react is that part with the double bond, and that's the functional group. And to name this, we have to consider the longest chain. In this case, we only have one single chain. It's a straight chain. Therefore, we can either, so we have two options. We can either name it from the left or we can name it from the right. If we name it from the right, we are trying to identify the position of the functional group, because that is the most important part of our molecule when we are trying to give an identity to it. So if we start from the right side, we are going to say 1, 2, 3, and that becomes the position of the double bond. If we start from the left, we are going to say 1, 2. So between those two options, we always choose the one that is the lowest number, or that places our functional group at the lowest position possible. So this compound has got 5 carbons, 1, 2, 3, 4, 5, and our double bond is existing on position number 1, 2. So I'm going to call it 2-pentene, or we can also just call it append 2 in. So it's either you start with the number or you place the number right between the T and the E. So the in part, which is the last part, is what identifies it as an alkene. The second compound, our functional group is indicated in blue again, which is that part, and it is the group COOH, and it is the functional group for carboxylic acids. When you are naming carboxylic acids, the carbon that is part of that functional group is always our carbon number 1. So starting from this carbon, it means that we are counting and we are looking for the longest chain, right? So it's either we are going to start from here and say 1, 2, 3, 4, 5, or say 1, 2, 3, 4, 5, but that is not the longest chain. So we try again 1, 2, 3, 4, 5, 6, right? So the longest chain in this compound is 6 carbons. That makes it a hexene, right? That's our parent name. Then we need to identify our substituent groups and their positions. And since we said that for carboxylic acids, the carbon that is part of the carboxylic functional group is always our carbon number 1. It means that starting from that carbon, we are saying carbon number 1, 2, 3, 4. So on position 4, we have these 2 methyl substituent groups. And our name is going to become 4.4 dimethyl hexanoic acid, right? So the parent name is the hexanoic part, or let me say the hexa part, which indicates that there are 6 carbons. Then the noic acid part is identifying our functional group. And dimethyl indicates that we have 2 methyl groups on position number 4 and number 4. So if we had another methyl on a different position, we're going to say perhaps 4.5. But because they are both on carbon number 4, we'll say 4.4 dimethyl hexanoic acid. The next functional group that we are going to look at is a carbonyl functional group. So it is the functional group C double bond O. And here, our functional group is existing. Let's identify the position. So we identify the longest chain. So we can either start from this side and we'll say 1, 2, 3, 4, 5, 6. But that is not the longest chain, right? Because we can say 1, 2, 3, 4, 5, 6, 7. So it means that we are taking this chain as our longest chain. And because it has 7 carbons, it becomes a hept group or a hept compound. Then we now want to identify the position of our functional group, right? And we can either start from this side and say 1, 2, 3, 4, 5. So it becomes position 5. Or we can start from this side and say 1, 2, 3. And it becomes position 3. And like I said, we always choose the number that puts our functional group at the lowest possible position. So it means that we are going to start from this side. So I'm going to go 1, 2, 3. So it's going to become a 3. And our carbonyl group in this case is a ketone group. And on this position 1, 2, 3, 4, 5, on position 5, we have another substituent group, which is a methyl group. So our name becomes 5-methyl 3-heptanone. So 5-methyl is identifying this functional group here, which is on position 5. And the 3-heptanone is identifying the ketone group as being on position number 3. And another way of writing this is by saying 5-methyl heptane 3-on, where the on part is the part that represents the ketone group. The next compound that we have is the functional group hydroxyl, right? The OH group. It's a hydroxyl group. And compounds that have got the hydroxyl group are called alcohols. And again, we are going to try to name this compound. And we need to identify firstly the longest chain. And let's say I'm going to start from the left. and we say 1, 2, 3, 4, 5, 6. That's one possibility. Or we can say 1, 2, 3, 4, 5. All right, so we choose the longest possible chain. So we're going with the one which is the straight one here, which has 6 carbons. So it's going to be a hex, right? Then we need to identify the position of our hydroxyl group. And to do that, we can either start from this side, and that will place our hydroxyl group on position 1, 2, 3, 4, 5. Or we can start from the right, and that will place our hydroxyl group on position 1, 2. And obviously, we choose the one with the lowest number. So we're going to start from this side. So our name becomes 4-ethyl. So the 4-ethyl is identifying the position of the ethyl group, xn 2-ol, where the 2 is identifying the position of the alcohol is on carbon number 2. And another way of writing this is by saying 4-ethyl 2-hexanol. So, whilst we're still on functional groups, I would like to mention some of the properties that arise from different functional groups. So if we look at the first compound, you would remember that when we started, we said that compounds that only have got carbon and hydrogens tend to be non-polar compounds. And the first compound only contains carbon and hydrogens, and therefore is going to be a non-polar compound. Whereas the other ones, as you can see, contain oxygen. All right. So the first compound is likely going to have the lowest boiling point because of the type of bonds that it can form. Because it is a non-polar compound, it forms the weaker van der Waals forces. Therefore, it's likely to have the lowest boiling point. Then, when you compare these other three, we'll notice that carboxylic acid has got a hydrogen, and so does the hydroxyl group. And because of that, it can form hydrogen bonding. But if we compare this carbon and that carbon, we'll notice that this carbon is bonded to 2 oxygens, and therefore it's going to be more polar than this carbon. And because of that, the hydroxyl group allows for stronger bonding, intermolecular hydrogen bonding, than is allowed for in the hydroxyl group. The ketone group, there is no hydrogen attached to this oxygen. So because of that, the ketone compounds, unlike these other two, can only form the dipole-dipole moments or a type of intermolecular forces, but it does not have the capacity to perform hydrogen bonding because this oxygen is not attached to hydrogen. So because of that, just by comparing the functional groups that we have, we can say that the pentene is going to have the lowest boiling point, but the carboxylic acid is going to have the highest boiling point, followed by the alcohol, and then comes the ketone, right? But lastly, the lowest one, the one with the lowest boiling point is going to be our pentene. The next definition that we are going to look at is homologous series. So a homologous series is a series of compounds with the same general formula. All molecules in this series will contain the same functional group. So this allows us to classify compounds that contain the same functional group into a series with increasing mass. So for example, this is a methane, that's an ethane, that's a propane. And next to that is going to be the butane, and we keep increasing the size of the compound. And what you notice is that they all contain the same functional group, which is the CH, CH bond, single bond. And these are alkanes. The next is going to be, that's a methanol, ethanol, propanol. The next is going to be butanol. And these are alcohols. And what you notice is that for the hydrocarbons, which are the compounds that contain only carbon and hydrogen, and we said that they are non-polar compounds which use van der Waals forces as their main intermolecular force. As we increase the size of the compound, meaning to say that as you go down the homologous series, you are increasing the size of the compound. And as you do that, you're also increasing the number of electrons that are available for bonding. So as a result, moving down a homologous series, as you increase the size of the compounds, you increase the strength of the intermolecular forces. Therefore, the boiling points are going to be increasing as you increase the size. And you also get the same for the substituted compounds. Even for the substituted compounds, as you go down the series, increasing the size of the compounds, you get stronger and stronger interactions between the molecules, and therefore you get stronger and stronger intermolecular forces, which results in higher and higher boiling points. Our next definition are isomers. So firstly, we'll start with structural isomers. Organic molecules with the same molecular formula but different structural formulae are called structural isomers of each other. Then our next definition is basically isomerization. Right? So isomerization is the process by which one molecule is transformed into another molecule with the same chemical formula but different atomic arrangement, and it's called isomerization. So you might have one compound that has got the same chemical formula, but you rearrange the atoms in the structure to create a different compound, right? And the different compound will have different properties, both chemically at times or physical properties, but they contain the same number of carbons or same number of hydrogens, right? But just different arrangement of the atoms. And two such compounds that contain the same formulae but have different structural arrangements are called isomers of each other. And what are some of the examples of isomers? So there are basically three types of isomerization that you get. And the first one is chain isomerization. And we have got one compound here. As we can see, it's an alkane. It has got 4 carbons, so it's a butane. And it is a single or a straight chain. But we can rearrange this to form a compound like that. And what you notice is that the chemical formulae of these two structures is the same. But we have rearranged it to put one of the methyl groups in the center or in the middle carbon to form what is called a branched compound. So here we have got the difference between a straight chain and a branched chain, and we call that chain isomerization. And if we are naming this compound, we are identifying the longest chain, which is going to be this chain with 3 carbons. So our parent name is going to be a propane, and we identify the position of the substitute group, our methyl group, which is on position number 2. And whether you start counting from the left or you count from the right, the position for this methyl group is always position number 2. So the name becomes 2-methyl-propane. The next type of isomerization is position isomerization. And with position isomerization, let's look at this compound. We'll notice that it has got 1, 2, 3, 4, 5 carbons, and it has got a substituent atom on position number 1, which is a fluoro atom. And we are going to call it 1-fluoropentane, right? It has got 5 carbons and it has got a substituent of a fluorine on position number 1. If we rearrange this compound by putting the fluorine on a different position, such as in this compound, where our fluorine is now on position number 2, and this compound is now 2-fluoropentane, what we'll notice is that we have rearranged or we have changed the position of the fluorine, and we call that position isomerization. So our third isomerization is the functional group isomerization. And if we look at this compound, it has got 3 carbons, and it is a carbonyl compound. But it is a special carbonyl compound called a formal compound. And the name is going to be propanol. So it's an isomer of this one, right? And what we'll notice there is that the CO bond is at the last or the end of the chain in the propanol, but it is in the middle of the chain in the propane 2-on. And these two are functional group isomers. And the difference there is simply the position of the functional group. And this one is an aldehyde, while this one is a ketone. So here I am displaying all the isomerization types that we get, and we said these are chain isomers, these are position isomers, and these are functional group isomers. And I would like to mention, whilst we are here, that when you have got chain isomerization, you get a difference in physical properties. So here I would like to mention some of the differences that arises from having different arrangement of the chain. So when we have got a straight chain, you can imagine it that we have got one straight chain and another straight chain. And they can bond properly because they can be pegged nicely one on top of the other. And there is a larger surface area for them to bond. And because of that, you get stronger bonding between the molecules, or stronger intermolecular forces when you have got a straight chain. And as a result, you get higher boiling point because of that. But when you have got a branched chain, you can imagine that, let's say we do that. So it is now branched, and the contact surface area is now smaller. And because of that, the intermolecular forces that can arise are going to be weaker, and you get lower boiling points. So one of the differences that you will get between chain isomers is that the straight chain will have higher boiling points, but the branched chain will have lower boiling points. Position isomerization, one of the differences that you get usually is the type of reactions that you get. So if you are reacting and you are trying to, as we shall look at later on, if you are doing a substitution reaction and you are trying to substitute this fluorine, as opposed to substituting that fluorine, you notice that this one is easier to access or to reach, but this one is in between atoms, so it is more difficult to access. So this one will give a faster reaction because the fluorine that you are replacing is not surrounded by too many atoms. So that's some of the differences you get when you have position isomers. And functional group isomers will also result in different physical properties. Your aldehydes versus your ketones will also, as you can see, this aldehyde has got a hydrogen bond between the carbon that is bonded to the carbonyl or the double bond oxygen, whereas this carbon does not have hydrogen bond. So the type of bonding that you get in the ketone are going to be the dipole-dipole moments, whereas for the aldehyde, you can use this hydrogen to form hydrogen bonds. So you get a stronger intermolecular forces in this functional group isomer as opposed to that functional group isomers. So isomers, even though they have the same chemical formulae, will have different physical properties because of the isomerization. Next, we are going to look at saturated versus unsaturated compounds. So what are saturated compounds? A saturated compound is only single bonds, and it does not have any double bonds or triple bonds. All carbon atoms are bonded to 4 other atoms. So you would remember that when we looked at the special properties of carbon, we said that carbon has the potential to form single bonds, double bonds, or triple bonds. When you have got a compound that only has single bonds, we call that compound saturated. And you can think of it as it is a full compound. There is no other place to put any additional atoms to it. And this influences the type of reactions that you get. Then you have got the unsaturated. So unsaturated, an unsaturated compound contains double or triple bonds. It contains one or more carbon atoms bonded to only 2 or 3 atoms. And in that case, we have got at least one carbon that has less than 4 atoms around itself. And we can regard it as not full because you can add another atom to one of the bonds. And some of the examples that we get are this is a propane, and we only have got single bonds. So all the carbons that we have are surrounded by 4 atoms, and all their bonds are single bonds. Next to that is a propene, which is an alkene, and our double bond is on position number 1. We start counting from this side because if we count from the other side, it will place our double bond on position number 2. But we said that we should always put our functional group on the lowest possible number. So we'll name it from the right, and it's 1 propene or a prop 1 in. Next is a propyne, which is an alkyne. And in this one, we have got a triple bond, right? We have 3 bonds between the 2 carbon atoms. So what you notice is that moving from the left to the right, we are removing a hydrogen atom. And our compound is becoming less and less saturated. So this is saturated, this is unsaturated. So this is full, all the carbons are surrounded by 4 atoms. Therefore, all the carbons you can say are full. Whereas moving to the right, some of the carbons are surrounded by less and less number of atoms, and we are increasing the number of bonds between the carbon atoms, and we get unsaturation. And you get different properties. If you look at these compounds, you notice that they all have 3 carbons, but because of this saturation, you get different properties. And your saturated hydrocarbons, they tend to be solids at room temperature, right? So saturated hydrocarbons, they form stronger bonds or they form stronger intermolecular forces. And one way to think about it is simply that intermolecular forces, they rely on the displacement of the electron cloud. So the more electrons that you have in a molecule, the stronger the intermolecular forces you can form. So when we start from propane, we have more hydrogens, but by the time we get to propyne, we have less hydrogens. So by removing hydrogens in each step, we are removing the number of electrons available to participate in intermolecular forces or bonding. So your saturated hydrocarbons, they tend to have higher boiling points, or they tend to be solid at room temperature. Then your unsaturated hydrocarbons, they tend to be liquids, right? Because as your unsaturated hydrocarbons, they tend to have lower boiling points or lower melting points. So those are some of the physical property differences that you get as you move from saturated hydrocarbons to unsaturated hydrocarbons. All right, so we are going to look at some application questions. And the paper that we're going to look at is paper 2, November 2016. And we're going to be looking at question number 3. So if you look at that paper, the first question is saying that the boiling points of 3 isomers are given in the table below. So we have 3 different isomers. We have got isomer A, isomer B, and isomer C. And they have different boiling points. I'm just going to draw the structures, the chemical structures of the 3 isomers. So if you look at the first isomer, we are told that it is a propane, that is the parent chain. So it means that propane, it has 3 carbons. So the longest chain has 3 carbons. But on position number 2, we have got 2 methyl groups. So position number 2, we have 1 methyl group there, another methyl group there. And we are going to fill in the spaces. With the hydrogen atom. So this is our chemical structure for the first compound. The second compound, the parent chain or the longest chain is a butane. right? So it has got 4 carbons. So we have 1, 2, 3, 4. And on position number 2, we have a methyl group. So I'm just going to start from the left. And position number 2, we have a methyl group. Then we are filling up the rest of the space, making sure that every carbon has got 4 bonds around itself. And that is our B. Then our C is a pentane, right? Pentane, 5 carbons. So 1, 2, 3, 4, 5. So these are isomers, meaning to say that they have the same chemical formula, but just different arrangements of the chains. And so going to the first definition, the first question, 3.1, it says define the term structural isomer. And a structural isomer, these are simply compounds with the same chemical formula but different structural formula, right? So the same chemical formula but different arrangement of the atoms to get a different structural formula. Second part, what type of isomers are these? They are obviously chain isomers. 3 says explain the trend in the boiling points from compound A to compound C. So you would remember that when we looked at isomers, we said that this is a branched isomer, this is less branched than this one, and this is a straight chain. And we said that a straight chain offers more surface area for intermolecular bonding with the next molecule. Whereas this one, it is smaller, and therefore it offers a smaller surface area or a contact with the next molecule. So because of that, we are going to get stronger intermolecular forces with the last compound C, and we are going to get the weakest intermolecular forces with compound A. And because of that, compound A is going to have the lowest boiling point, and compound C is going to have the highest boiling point, which is what we are observing here. So if you are explaining this, you can either explain it starting from the straight chain. So we are saying compound C is a straight chain. That's the first point. Because it is a straight chain, it offers a longer surface area or a bigger surface area for intermolecular forces. And because of that, it produces stronger intermolecular forces, and because of that, it produces a higher boiling point. And as we go from C to B to A, we are reducing the surface area. They are becoming less and less straight. So they're becoming more and more branched. So if we consider it from the straight chain, we will say that the straight chain is less branched. It has a longer chain length, larger surface area for intermolecular bonding, which creates stronger intermolecular forces. Therefore, more energy is required to break the intermolecular forces, which creates higher boiling point. Or you can look at it from A and say that A is more branched. Because it is more branched, it has less surface area for intermolecular forces, creates weaker intermolecular forces, which require less energy to separate or to separate, yes, and therefore creates lower boiling points. And as we move from A to B to C, they become less and less branched. So you can look at it from both ways. Then number 3.4 says which one of the 3 compounds, A, B, or C, has the highest vapor pressure. So the relationship between boiling point and vapor pressure is that as you increase the boiling point, you reduce the vapor pressure. So vapor pressure is simply if you have got a liquid and the liquid is evaporating, right? So it is converting the liquid to a gaseous state. And as the gaseous molecules rise from the liquid, they press pressure on the lid, and that is basically vapor pressure that is coming from the vapor that has evaporated. So if you have got a liquid with a low boiling point, it means that at any given temperature, you have more evaporation happening because the liquid has a low boiling point. So as a result, the lower the boiling point, the higher the vapor pressure. So in this case, they're asking us which one is the highest vapor pressure. So the one with the lowest boiling point is the one with the highest vapor pressure. So our compound A is going to be the one with the highest vapor pressure because it has the lowest boiling point. Then 3.5 says use chemical formula to write a balanced equation for the complete combustion of compound B. So compound B, we are just going to use our structures to calculate our number of carbons. We have got 1, 2, 3, 4, 5 carbons. And our hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. So every time you have a combustion reaction, it means you are reacting your organic compound with oxygen, and you always form carbon dioxide and water. Those are the two products that you produce if you combustion or if you burn a hydrocarbon. So we are adding oxygen, and we are going to get carbon dioxide plus water, and you need to balance it. So to balance it, it's usually easier to balance it if you leave out the oxygen and balance the other atoms first. So we have got 5 carbons, and on the left hand side, it means that on the right hand side, you also need 5 carbons to balance the carbons. So we are going to add a 5 there. Then we go to the hydrogens. Right, we have got 12 hydrogens on the left hand side, and on the right hand side we have 2 hydrogens. So we need to multiply those 2 by 6 to make them to be 12. So it means we are putting a 6 there. And then lastly, we are going to balance the oxygens. So to balance the oxygens, here we have got how many oxygens? We say 5 times 2, that's 10 oxygens. This side we have got 6 times 1, 6 oxygens, so we have a total of 16 oxygens. But in our chemical formula for oxygen, we already have 2 oxygens. So we need to multiply that 2 by a certain number to make them 16 oxygens. And that number obviously is an 8. And this will be our balanced chemical equation. So we're going to do our second application question, and this one is coming from a March 2018 paper, paper 2 again, question 3. So the question says study the vapor pressure versus temperature graphs for 3 organic compounds X, Y, Z below, which belong to different homologous series. Atmospheric pressure is 100 kPa. Right, so here we've got a graph which is showing vapor pressure on our y-axis and temperature on our x-axis, and we are told that our atmospheric pressure is 100. So remember we said that when you evaporate a liquid, you are converting the state from liquid state to a gas state. And once the gas forms, the gas will rise from the liquid going up. But for every liquid state, there is atmospheric pressure that is pressing down on the liquid. And the gas can only rise if it creates enough pressure to overcome the atmospheric pressure pressing down. So at the moment where you have enough vapor pressure created to equate or to equal the atmospheric pressure, at that point you have boiling point. Because that's the point where the vapor pressure is equal to the atmospheric pressure, and that allows the vapor to then start evaporating going up. So it simply means that at the point where the vapor pressure of these different compounds gets to 100 atmospheric pressures, the boiling point has been reached for each one of them. Question 3.1 says write down the vapor pressure of compound Y at 90 degrees Celsius. Right, so if we look at our x-axis where our temperature is, we'll notice that our scale per each graduation is 5 degrees Celsius. So it's going 0, 5, 10, 15, 20, 25. So we have to identify where our 90 degrees Celsius is on the x-axis. To do that, we look for the closest number closest to 90, and maybe we can start from 75 or 100. So starting from 75, we'll say 75, 80, 85, 90. So our 90 is here. And we are looking for the vapor pressure for compound Y, so this is the graph that we are interested in. So we'll draw a straight line from 90 degrees Celsius to that graph, and then once we get to that graph, we'll draw a horizontal line to the y-axis, and we'll notice that the vapor pressure that aligns with temperature 90 is 150 K. So our vapor pressure here is going to be 150 kilopascals. Then 3.2 says the graph can be used to determine the boiling points of the three compounds. Define boiling point. So boiling point is simply the temperature at which, I'll just read off from here. So the boiling point is simply the temperature at which the vapor pressure is equal to atmospheric pressure, and I've explained the dynamics between those two. Then next it says determine the boiling point of compound X. So we said that boiling point is reached when the vapor pressure is equal to the atmospheric pressure, right? And we were told that the atmospheric pressure is 100 kilopascals. So this time we are going to 100 kilopascals, and we are looking for the boiling point of compound X, which is this graph. So we are drawing a horizontal line up to the graph for compound X, which is that one. Then we draw a vertical line to the x-axis there, and you'll notice that it is getting to where the temperature is. This is 50, so this is going to be 55, right? Because we said our units are 5 degrees per graduation. So our boiling point is going to be 55 degrees Celsius. 3.3 says the homologous series to which the three compounds of similar molecular masses belong were identified in random order as alcohol, carboxylic acid, and ketone. So these are the three compounds that are represented by X, Y, Z, but not in that order. We're not sure yet which one is which, right? So which compound X, Y, and Z is the carboxylic acid? So you'd remember when we looked at functional isomers, we indicated that when we have got different functional groups, we are going to get different boiling points because of the type of intermolecular forces that you get. And we said that different functional groups will create intermolecular forces with different intermolecular forces strength. And you'd remember that we said carboxylic acids have the strongest intermolecular forces between these three, right? Because we said that carboxylic acid can form hydrogen bonds between one carboxylic acid and another, and so can alcohols. But we said that because in carboxylic acids the carbon is bonded to two oxygens, then the polarity for that bond is stronger. Therefore, you get a strong hydrogen bond in carboxylic acids than you get in alcohols. And we said ketones, there is no oxygen attached to there is no hydrogen. And for ketones, we said that there is no hydrogen attached to the oxygen. Therefore, it does not form a hydrogen bond using that oxygen. But the ketone can still form dipole-dipole moments or intermolecular forces. So between these three, we already know that carboxylic acid is the one with the highest boiling point, followed by alcohol, and then lastly, our ketones. So which compound is the carboxylic acid? The compound that is carboxylic acid is going to be the compound that is the highest boiling point. You notice that compound X is the least boiling point at 55. Compound Y is somewhere there, which is around 80. And compound Z is even beyond the page. So it has got a boiling point which is more than 125. So compound Z is going to be our carboxylic acid. So atmospheric pressure is given as 100 kilopascals. So we are going to put our ruler at 100 kilopascals on the y-axis. And moving across, we will meet our first compound, which is X, with a boiling point of around 55. And our second, which is Y, with a boiling point of around 80. And then the one with the highest boiling point of around 117 is going to be compound Z. So that identifies compound Z as our carboxylic acid. Then 3.3.2 says explain your answer to 3.3.1 by referring to the type of intermolecular forces in compounds of each of the homologous series above. So I'm going to just show you an example of carboxylic compound. So just imagine that this is carboxylic compound 1, carboxylic compound 2, and carboxylic compound 3, and they are in solution. So between these two carboxylic acids, or let me start with these two, right? Between these two, we can form intermolecular forces across like that, right? So this is the hydrocarbon part, which is nonpolar. And we can form nonpolar intermolecular forces, or van der Waals forces, across the length of the carboxylic acids. And this is one type of bonding that we get. But because it's a carboxylic group with this functional group, it can also bond to a next carboxylic acid using the functional group part, whereby we can form a hydrogen bond between this oxygen and that hydrogen, and we can form another hydrogen bond between this oxygen and that hydrogen. And when we bond these two carboxylic compounds, we can call these dimers. So it simply means that we have got two of these compounds which will be bonded together using the hydrogen bonding, and that adds to the intermolecular forces that we say the van der Waals that are happening along the length of the carboxylic acid. So on top of this one, we have got what? Hydrogen bonding, which makes the intermolecular forces between carboxylic compounds to be all the more stronger. Whereas we can also form hydrogen bonding in hydroxyl compounds or alcohols, but they are not going to be as strong as the ones that we form in carboxylic acids. When we look at the ketone, we do not have this type of hydrogen bonding in ketone, but we do have these intermolecular forces in ketones. So moving from carboxylic acid, going to alcohol and then to ketones, you realize that with carboxylic acids, we can form hydrogen bonding in addition to other intermolecular forces. And they also form dimers using the hydrogen bonding. And because they have the advantage of utilizing those two different types of intermolecular forces, they are the strongest of the three. Then with the alcohols, they can form hydrogen bonding on top of the intermolecular forces, but they do not form dimers as happens in carboxylic acid. So they are slightly, the intermolecular forces or the total of the intermolecular forces are slightly weaker in alcohols compared to in carboxylic acids. Then when you move to ketones, they cannot form this type of hydrogen bonding because their oxygen is not bonded to a hydrogen, as you would remember the structure that we looked at. So, but they do have dipole-dipole moments as one of their intermolecular forces, in addition to the non-polar intermolecular forces, van der Waals, that happen across the length of the chain, right, of the molecule. So because of that progression, you will notice that carboxylic acids, they form the strongest intermolecular forces, followed by alcohols, and then lastly ketones. And therefore, these ones will have the highest boiling point, followed by alcohols, and then lastly your ketones. Then we move on to 3.3. And it says compound X has 3 carbon atoms per molecule. Write down the IUPAC name for compound X. So we already know that our compound X is the compound with the least boiling point. Therefore, our compound X is our ketone. And we are now told that compound X has got 3 carbons. So it has got 1, 2, 3 carbons. And so it is a ketone with 3 carbons, meaning to say that it has got the carbonyl functional group. And for ketones, the carbonyl functional group is found in the middle, right? It is not going to be at the end. We said that you would remember it's only for aldehydes where the carbonyl group is found at the end of the chain. For a carbonyl, for a ketone, our carbonyl group is going to be right in the middle. So we're then going to have our hydrogens there. Our hydrogens there. So because our parent chain has got 3 carbons, it means that we are looking at a propanol, right? So it's going to be propanone. And we do not necessarily, we can say propane 2-on, but because it has 3 carbons, there is no other position for this functional group to be at except for position number 2. So you can write it like that, but even if you write it like that, both are going to be correct. So this marks the end of our application number 2.